Good morning. So I'm sorry I'm not there. It just seems like all this training is coming at the same time. So I have a lot of kind of theory to do with you today, and there's not a huge amount of calculation, so it's actually no harm. Obviously now if there's any questions, just let me know. So I am in tomorrow, please God. And I just want to remind you about the work that is due. Okay, so there's a couple of questions due that should be uploaded to Schoology. So I just had a look there, and some of it is, but most of it isn't. So, higher level, there should be this question uploaded to Schoology. Okay, and there's also, where's that? Oh, actually, sorry, it's down here. This higher level question. Okay, so there's this higher level question and then this higher level question. Yeah? So is that okay? There's two separate things on Schoology for that. And then for ordinary level, Devon, you owe me 3 questions. So this one here, and then both of these, the train and this. Okay, so that's 2 questions the higher level students owe me, and 3 questions, Devon, that you owe me. And I'm going to take them up tomorrow. Okay, so the plan is you won't have homework tomorrow, and I'm going to take them up. Like the only homework you're going to have is a paper question. But I'm hoping to be able to take that up and you just do your paper question and upload it yourself. Okay, so now, so we're nearly done with sound. We've gone through kind of what is a sound, the way sound proves it's a wave, so the wave phenomenon. So we went through reflection of sound, refraction of sound, diffraction of sound, interference of sound. There's an experiment that accompanies interference of sound, which I showed you. We didn't do ourselves, but I did show you the video. We talked about the fact that sound is both a mechanical wave and a longitudinal wave, and there's an experiment to prove that sound is a mechanical wave, which is this one here, the bell jar. This little piece here is connected with refraction. So this is because of the difference in the air temperature on a warm day versus a cold night. You get slightly different refractive indices. So the sound that's traveling thinks it's traveling through 2 different media, and as a result, it travels slightly faster in the warmer medium, and you get a bending of the wave either up or down depending on which part is cold, and that's why we can hear better on a cold night. The last day we were talking about harmonics or overtones, so that they're technically the same thing, but sometimes the naming convention is a little bit confusing. But we did see the video on the natural frequency, and then the first overtone, and then the second overtone, and you can continue to draw those standing waves. We talked about loudness and how amplitude affects loudness. So if you get a bigger amplitude wave, that sound will be louder. And then if you get a higher frequency wave, so more waves per second, that will be a higher pitch. Okay, so the wave language is bigger amplitude, higher frequency. The reality normal language is louder and high pitched. Okay? The quality is why we were talking about the overtones. So when you hear 2 identical notes played on different instruments, it's because one will contain more overtones than another. Okay, so a note played on a piano will include maybe the fundamental frequency plus 2 overtones, whereas the note played on a tin whistle will only be the fundamental frequency. So you get a different quality of sound, and that's how you can tell that one is a tin whistle and one's a piano. Okay, now the frequency limits of audibility. So they have like things here, like definitions. You don't need a definition of this. The frequency limits of audibility is literally the limits that you can hear. So the human ear can hear between 20 hertz and 20,000 hertz. And what you will find is that that limit will decrease, or that range will decrease as you get older. Like no more than eyes, you'll notice that people as they go into their 50s and 60s, people that never needed glasses in their life start needing glasses for reading or looking at a computer screen. It's similar with hearing. So you're hearing literally just by using your ears and by, listening to things over the years, your ears sort of get damaged, I suppose, as life goes on. Depending, like you'll find somebody who's in a band in their teenage years, their hearing will degrade much quicker than somebody who wasn't in a band in their teenage years. Or like people who listen to really loud music in headphones. Again, if you compare somebody who listens to really loud music in their headphones compared to somebody who doesn't listen to really loud music in their headphones, you get a degradation quicker. Do you know what I mean? So it's literally wear and tear. And I don't know if you've ever seen those things before where you play these high-pitched sounds, and if you do it in a room with various like generations of the same family, so if you have like, I don't know, you and your grandparents and your parents and maybe younger siblings, and if you play the sound, it just keeps going up. And what you find normally is that the oldest person in the room will not be able to hear a particular frequency, but you can still hear it. And then, that would be the grandparents, and then maybe the parents will drop out a couple of frequencies later, but you can still hear it, and so on. So they use it as a deterrent at like, spots where people would hang around, like outside shops or outside churches or, things like that they actually play this really high frequency sound that's really annoying, but it's only annoying to younger people. So it's literally to deter teenagers from hanging around, because older people can't hear it, so it doesn't bother them, and they wouldn't be hanging around anyway. So it's played at a frequency that most teenagers can hear, and as a result they don't stay there because it's an annoying sound to them. So that's the frequency limits of audibility. And then there are some animals, dogs, bats, dolphins, I think, that can hear what's called ultrasonic. So that's like that's above what we can hear. So you can get dog whistles. I don't know if you've ever come across dog whistles, but if you get a dog whistle and you blow a dog whistle, it sounds like nothing to you, but your dog's gone bananas. You can get these, it's really mean, but you can get these things on like YouTube and stuff, and you can play it for your dog and you can hear nothing, but your dog is going like demented in the corner. But yeah, that's because they can hear above 20,000 hertz and we can't. Okay, so the natural frequency of vibration, we were kind of talking about that when we were talking about standing waves. So the guy in the video that was setting up all the different standing waves, he had a particular string, and that string was tied at a particular length. And then when he started it up, I think the natural frequency for that string was like 8.5 hertz or something like that. And that's how he was able to set up the standing wave. Now, if he used a different material in that string, or a shorter string or a longer string, he would change the natural frequency. So essentially, like when you pluck the string, what is the natural vibration of that string? Okay, and that's the natural frequency. Sometimes called the resonance frequency. Okay, but it's the natural frequency for that particular whatever it is. Like it could be, remember at the start of this I was saying that something vibrates in order to create a sound. So literally everything has a natural frequency that it will tend to vibrate. Like if you take glass and you like flick the edge of the glass, that ringing sound, that's that glass's natural frequency. Yeah, and then you can mess with that by putting water in it. Have you ever seen people play glasses? So you can mess with the natural frequency if you put water in it. So the empty glass has a particular natural frequency that it will vibrate at if you get it to vibrate. So you can flick the edge of the glass, or what people do when they play glasses is they like wet their finger and they rub the edge of the glass, and that gets it to vibrate. But yeah, you can change the frequencies. That's why they can play them, because they can get it to be slightly different frequencies, so it sounds like different notes or whatever. So that's what natural frequency is. It's basically if you were to take something and get it to vibrate, the frequency that it tends to vibrate at, that's its natural frequency. Now, resonance. Okay. Resonance, by definition, is the transfer of energy between two objects with the same natural frequency. Okay, that's your definition. So for your exam, that's your definition. There's a definition down here, but it's, okay? It's just hard to learn. That's a better one. Transfer of energy between two objects with the same natural frequency. So pushing someone on a swing, I'm assuming at some point in everyone's life they've pushed someone on a swing, or at least you know the mechanics of it. So the idea of pushing someone on a swing is that they want to go higher. So if you put a kid on a swing and you want to push them, the idea is that you want them to go higher and higher and higher, until they get scared. You know what I mean? So the way we do that is we match the natural frequency of the swing with our push, right? So the child is swinging. This is hard when I'm not here, but the child is swinging. I'm going to try and do it. The child is swinging like forward and back. This is going to come up as a big chunk. Sorry. Forward. Okay. So anyway, that's the idea, right? The child is swinging, if you listen to me, forward and back and forward and back. And what we want to do is we want to push the child in a similar rhythm, right? So the child goes forward and back, and when they come back to us, we push them. And then they go forward and back, and we push them. So it's like, over, back, push, over, back, push, over, back. So we push them as they're arriving back to us, about to start a new swing. So one full oscillation for them, as in swing forward and back. We're going to push them every time they come back to us, right? So if you were looking at a cycle per second, the swinging child has a cycle of over, back, and our cycle is a push for each one of those over backs, right? So we're on the same frequency. Okay, I'm going to lean forward and come back to push them as they're swinging over and swinging back. Okay, if you miss that rhythm, right? If you push, so if they're swinging over and back and you're following them and pushing them and pushing them and pushing them, and you're not matching their swing, they won't get any higher. But if you wait on that push and you match their frequency, they will get higher with every swing. Okay, and what's happening there is a transfer of energy between you and the swing. And the reason that's happening is because you have made it so that you are at the same frequency as the swing. Okay? If you knock off that frequency, if you don't wait until that moment when they come back to you and they've completed their cycle and you're going to start your cycle, if you don't match that swing, what you will do is you will decrease their amplitude. Okay? So if you get this right, you get an increase in amplitude, which for the kid in the swing is what they want. Yeah? They want to be pushed higher and higher and higher. So what you are doing by doing that, by matching your push to their swing, or matching the frequency of your push to their swing, which means every time they do a full swing, you do a push. If you can get that to match, what's happening is resonance, and resonance is where you get an increase in the amplitude. Okay? There's an experiment that goes with this, just a little silly experiment that goes with this, where you have a block, and on the block you've got a couple of tuning forks. Okay, and the tuning forks are at different frequencies. So say this one is 256 hertz. This one is, I can't remember another one, is it 280 maybe hertz? And this one is 512. Okay, so you have three different frequencies. Sorry. So what happens then is you come in with another one that's 256. You bang it off the table and you get it to vibrate, so it makes a ringing sound. And if you bring this over close to these, what you will find is that this one will pick up the vibration. Okay, so you don't strike this one, but because the two of them, this one out here and this one in here, because they're at the same natural frequency, because the natural frequency of those tuning forks is 256 hertz. So because they're at the same natural frequency, if you strike one of them and bring it close to the other one, there'll be a transfer of energy between them. And what will happen is this one here will start to vibrate even though it wasn't vibrating before, because it has picked up the energy from this one out here. And that's a demonstration of resonance. The other two don't pick it up because they don't have the same natural frequency, but the one with the same natural frequency picks it up. And you can knock the tuning fork and bring it in, like put it right beside the 512, and it won't pick up any vibration. Put it right beside the 280, it won't pick it up. But if you put it beside the 256 and stop the original one, stop that one, like literally use your hand to stop it vibrating, you'll find the sound continues because the one over here is now vibrating. Okay, because you got that transfer of energy because of the matching frequencies. So there's a couple of like interesting ones here you might have heard of before. So like this one here, someone shattering a glass with singing. So it is true. Basically, the glass has a natural frequency that it likes to vibrate at. And then if the person's singing, that's an I don't know, singing person. I can't draw, you know that. If the singing person's frequency matches the natural frequency of the glass, so if they match, then you get a transfer of energy. The transfer of energy causes an increase in amplitude. So what's happening then is that the glass is vibrating bigger because that's an increase in amplitude. And it can't take, glasses aren't designed to do that, so it can't take that increase in amplitude, so it shatters. Happens sometimes, they actually allow for it now here, buildings in an earthquake. That happens sometimes where the vibration that's caused by the earthquake matches the natural, because like if a building is set vibrating like a gusty wind or something like that will set a building vibrating. A building does sway, and they're built to like allow for a certain amount of sway. But what can happen with an earthquake is if the earth quakes, so you've got the earth like literally vibrating up and down. So if the earth vibrates up and down and it happens to match the natural frequency of the building, then that will cause a transfer of energy, which causes an increase in amplitude. So now you've got a building that instead of swaying within the natural limits, it's going to be swaying much more because of that increase in amplitude. And if that happens, then the building collapses. So now in earthquake-prone places, they've actually engineered, over the years, they've managed to engineer buildings that can sway an awful lot more than they would have been able to like 100 years ago or 200 years ago. So they have a much bigger sway to allow for this. And there's an example down here, the Tacoma Bridge in America. Is that the one? No, I thought it was in France. Yeah, here. This is the one in 1850, the French soldiers. So French soldiers were passing over a bridge, and now these days soldiers, when they're in march, so you know, like 1 2 1 2 1 2, so if they ever have to march across a bridge, what they do is they break step, so the soldiers that are in front continue 1 2, and the ones that are second go a half step off them, right? So that they're not all going 1 2 1 2 1 2. Because what happened in 1850 was that they were doing their 1 2 1 2, which had a frequency. There's a frequency to that step, and it just so happened to perfectly match the natural frequency of the bridge, which caused an increase in amplitude. The bridge started to vibrate, and the bridge collapsed. And they killed, does it say it there? Yeah, 226 of them were killed because they fell from the bridge. And it was because their step created a frequency which matched the natural frequency of the bridge. Resonance occurred, so there was a transfer of energy between the soldiers and the bridge that caused an increase in amplitude of the bridge. The bridge wasn't built to vibrate like that, so it collapsed. So now when soldiers march, if they reach a bridge, they knock out of step. So there's a command and they walk out of step to avoid that perfect 1, 2, 1, 2, which could potentially cause a vibration in the bridge. Okay, so that is resonance, and that's a very, very, very important concept. Okay, so will you take down your notes on that one, please? On the frequency limits of audibility, natural frequency, and obviously resonance connects with natural frequency. A little diagram of this experiment would be great, and then a couple of examples of resonance. The glass and the opera singer is the easiest one. I just find this one kind of easy to remember. Yeah, I think we'll talk about threshold frequency and that tomorrow. And that kind of brings us into the experiments, which I'm like, for now, like I said, I'm only going to be able to show you.